Today we're going to talk about carbocations. As a Lewis structure, it was okay, in terms of exceptions, for carbons to only have 3 bonds, no lone pairs, and a positive charge. These carbocations, turns out, are not very stable in themselves and are usually reactive intermediates. So we're going to address 3 different things in this tutorial. How are carbocations formed? Are all carbocations equal? So, if not, why not? And finally, what do carbocations do? Okay, so first, in how carbocations are formed. There are a number of ways to do this as part of a chemical reaction, but the one that we are introduced to in chapters 6 through 8, and including in Chem Activity 8A, is carbocations are formed as an intermediate in a reaction between an acid, protic acid such as HBr, and a on the carbon-carbon pi bond. So if this pair of electrons were to act as a base, grab an H+, kicking out an HBr bond, leaving the electrons behind on bromine, we would end up with a bromine atom, would have 1 bonus lone pair of electrons, with a net negative charge. Meanwhile, the carbon-based species, which is always the most important to us as organic chemists, has lost a pi bond, and in its place, that pair of electrons that used to be part of the pi bond goes to make a sigma bond with the proton. So this could be classified as both a Bronsted-Lowry acid-base reaction, with this being the base proton acceptor and HBr being the proton donor, or it could be classified as a Lewis acid-base reaction, with the pi bonding electrons acting as the electron donor pair and the proton acting as the electron acceptor pair. In either case, we end up with a new bond between carbon and hydrogen. We also end up with a carbon that has 3 sigma bonds and 1 no pairs of electrons, which would give it a net formal charge. And like all balanced equations, there is no net charge on the left-hand side, there is no net charge on the right-hand side. So the carbocation is in fact formed by reaction of a neutral alkene and a neutral HBr, which might have a low energy like so. And in the process, you've taken 2 neutral things and made 2 charged entities, higher energy. Overall, the process shown to create the carbocation is endothermic, and the activation energy to get there would be even higher than the energy necessary to make the positive and negatively charged intermediate ions. This endothermic process would not occur by itself unless there were a subsequent exothermic process. And that subsequent exothermic process should be pretty obvious. There is an electron deficient carbocation, Lewis acid. There is an electron excess, Lewis brace bromide, and that bromide would provide a pair of electrons to make a new bond. And in a second step, carbon, in addition to our original sigma bond between the hydrogen and the other carbon. In other words, in 2 steps, we've managed to go from a double-bonded alkene and an HBr to 2 new sigma bonds between H and Br and the 2 adjacent carbon atoms that used to be the 2 carbon atoms of the pi bond. The second step takes charged intermediates, the carbocation and the bromide anion, and neutralizes them. It is a net exothermic process. In fact, after the addition of HBr to a pi bond, the overall system is lower in energy than it was to start with. It is a net exothermic process. However, the first step is endothermic, where it takes energy to get to that carbocation intermediate right here, and the activation to get energy to get there is even higher than the energy it takes to get to the intermediate. In this chem activity, we spend a lot of our time talking about the first half of this reaction because it is very important in terms of energies and reaction outcome. In order for the first step to happen, we have to have enough energy to get over the activation energy of the reaction, like so, to get to this high energy intermediate. And anything that affects the energy of the intermediate will also affect the energy of the transition state, which is close in both energy and structure to the intermediate. So, for example, if there was more than one way to form a carbocation, one of them might be higher in energy to form than the other. The intermediate would be higher in energy, and the activation energy would be higher. Okay, so a lot of the chem activity focuses on what makes one carbocation more stable than the other, because it turns out they're not of equal stability. In particular, tertiary carbocations are more stable than secondary, which are more stable than primary. And in general, if there is conjugation involved, cations are more stable than if there isn't. And by conjugation, I mean you can write resonance structures, and I'm specifically talking about the allylic and benzylic systems. Allylic is when you have a carbocation on a carbon adjacent to a CC pi bond. Benzylic is when you have a carbocation adjacent to the pi bonding system in a benzene ring. Okay? So if we were to classify these, of course, back from our previous lessons, anything that has a carbon with no other bonds to carbon is called a methyl group. Anything with only one other bond to carbon is a primary carbocation, which is less stable than a secondary carbocation, which is less stable than a tertiary carbocation. Okay, let's talk for a minute about how this could be so. So, for example, the electrons in this CH sigma bond could stabilize empty p orbital on the carbocation next door. This process, from which a little bit of electron density is shared between a sigma bond, big lobe on the front that forms the bond to hydrogen, small lobe on the back, into the empty p orbital on this carbon. So sigma bond to p orbital stabilization is often called hyperconjugation. It's not real conjugation. You can't draw resonance structures for it, but it does show electron delocalization. And the more of these adjacent CH or C something bonds next door, the more stabilization you have. Compare that to having just a sigma bond, like on this methyl cation on the left. There's a sigma bond here. There could still be a p orbital, empty p orbital, but the hydrogen that's bound to this carbon has nothing here. There's nothing above or below that can donate electron density into the empty p orbital. So that is why the more hydrogens you have, the less stabilized the p orbital, the less stabilized the carbocation. The more carbons you have adjacent to your carbocation center, the more carbon other thing bonds, carbon hydrogen or carbon carbon bonds, the more stabilized that carbocation will be, leading to tertiary being more stable than a secondary, more stable than primary with only one carbon next to it, more stable than methyl, least of all. Now, in terms of allylic and benzylic, we have actually built-in stabilization through the p-pi orbital system. For example, in an allylic system, you would have the pi bonding electrons. Those two electrons are actually shared between the three p orbitals. And for the allylic carbocation, we can actually draw two resonance forms. Likewise, the p orbital of the benzylic system down here is stabilized by the ring next door. So what does all this mean in terms of energy? Well, if I had a propene molecule, okay, and I were to react it with HBr, for example, the pair of electrons from the pi bond on the propene that grabs onto the H plus, kicking out the Br minus, could theoretically go in one of two directions. It could go to form a new sigma bond between the first carbon atom and the hydrogen, or could go to form a sigma bond between the middle carbon and the hydrogen. The primary difference between these two structures is where the positive charge ends up. In the second example, the positive charge ends up on the primary carbocation position, and in the first example, the carbocation ends up in the secondary carbocation position. So secondary versus primary. Energetically, these are quite a bit different. We know that we start from a common energy point. In the low energy starting materials, it's the same set of starting materials for both of them, to the high energy secondary carbocation and the even higher energy primary carbocation. The pathway to get to the primary carbocation goes through an activation energy that's a little higher than that, and the pathway going to the secondary carbocation. Secondary is more stable than primary, and so secondary is going to be formed faster than primary. I often think of this as riding a bicycle uphill. If you had two ways to get to an uphill destination, you're going to choose the one with the lower activation energy rather than the higher activation energy. So in fact, the secondary carbocation is formed preferentially, and this is the pathway that will occur.